continuing here, section 3.1. This is video part 2. Where we just left off was right here with the properties of exponents. We got through those, and so now on the next slide, regarding the function 2 to the negative x. Now, we previously did say that that's equal to 1 over 2 to the positive x, according to our properties here, right there. So this function, if I write that out, that's 1 over 2 to the positive x. Well, this is going to be the same thing as taking 1/2 to the x power. Because 1 times 1 times 1 times 1, as many times as you have to do that, it's still going to be 1. Really, all you'll be doing is taking the denominator and taking it to the x power. So with that in mind, now that you see that 2 to the negative x can also be written as 1/2 to the x power, take one moment to write f of x equals 4 to the negative x in a different way. Pause the video and resume when you have something, and hopefully we get, since 4 to the negative x is equal to 1 over 4 to the positive x, this is the same thing as 1/4 to the power of x. So this here is another name for that. They're the same exact things. These graphs can be thought of as transformations, just like we've seen with parabola and other types of graphs. The same basic properties are going to apply here. So what we're going to do is look at 4 different scenarios here. All of these are going to be thought of as a transformation of some sort from the original graph 2 to the power of x. And just to bring your mind back to it, 2 to the power of x is the graph that we first graphed. That's the one here that's in green. Okay, 2 to the power of x is this one in green. So what's going to happen if we have 2, instead of 2 to the x, now we have 2 to the power of x plus 1. Well, what this is really is it's f of x plus 1 is really what it is. Because instead of taking 2 to the x, now if this was x plus 1, that would be x plus 1. We'd have exactly this thing. Well, we saw in a previous chapter, actually a previous chapter and within a section, that this equates to the original graph being shifted left one place. Other than that, it's the same exact graph, just located somewhere else. We can quickly show that if we go to y equals and we start with the original 2 to the x. I'll just do this under a standard window for now. And I compare that to 2 to the power of, but this time I put in parentheses, x plus 1. We should see the same graph, except it's located left. Okay, that's actually just a horizontal shift right there. Okay, the second one here, what we have is, this is the same thing as having f of x plus 1. F of x being the original 2 to the x. Well, if we think back, what that means, this is just going to be a vertical shift. We're going to take the original 2 to the x and it's going to get shifted up 1. I'll quickly demonstrate that to you. So we'll say this is going to be 2 to the power of x, and then not in the parentheses, we put plus 1. You should see that this graph goes up one spot higher. Other than that, it's the same exact graph. So we can clear that out of there. Now this guy here, negative 2 to the x. What we have here, this is the same exact thing as negative f of x. And if we think back, that's going to be, it amounts to a reflection in the x-axis. Oops. Reflect f of x across the x-axis. So in other words, if I plugged in a 2 into this function, I got 2 squared is 4. Now when I plug in a 2, this becomes negative 4. So instead of plotting that point up above the x-axis, we're going to plot it down below the x-axis. So that demonstrates the reflection there. And then our last one is 2 to the negative x. What this is, it equates to we have f of negative x. All we did was we changed this from an x to a negative x. And what that is this going to reflect the original graph across the y-axis. So a demo of that. So I don't think I showed you negative. Let me show you the third one here. I skipped that one. Negative 2 to the power of x typed in just like that. Should be a reflection across the x-axis. There it is. And let's get rid of that. And let's insert that negative there instead to show you number 4 is reflected across the y-axis. And you can see that's what that does. Now the natural base, e. E is an irrational number. It's approximately equal to 2.718281,828. But we can't, it doesn't ever terminate. Just like all irrational numbers, it cannot be written as a fraction of 2 integers. So it's a value that we don't have an exact value of, like every irrational number. So instead we use a symbol, just like we use pi. Here we use e. A lot of people get confused and think that this is a variable, but it's not. It's a constant. Now, one thing that we are going to demonstrate here is that when x becomes a really big number, then e to the x can be approximated by this. And this will come into play a little bit later on. What I'll do is I'll give you a quick demonstration of this real quick. So in our calculator, I'm going to bring up, let's just clear this. Okay, the first one I'm going to put is I'm going to graph y equals e, which is, oh, where is it? Is that e? No, that's not e. It's below it. I hit the wrong button. So e to the first power is the same thing as just e. So we'll see a horizontal line here at 2.718, whatever it is. Now what I want to do is beneath it, I'm going to put 1 plus the fraction 1 over x. I'm going to put that inside of another parentheses. Close, close. And I'm going to take that to the x power. So I'm typing in that function. Now, for large x values, you can see that this is an asymptote here. So the further I go to the right, the closer it's going to get to that line. So for large x values, this is a good approximation. Now, where that'll become useful is when we talk about compound interest, and so we'll begin that discussion right here. So here's some applications for the stuff that I've been showing you here. And again, I hope you've seen some of this before. So let's see. First off, we have a problem that is $2,000 gets thrown into an account. It's going to earn 5% annual interest. That means once a year we're going to add 5% because it's compounded annually. Annually meaning once a year. So at the end of your first year, you get 5% added on to 2,000. That becomes a bigger number. At the end of that next year, that new number gets increased by 5% again, and it keeps on going. Well, how do you increase by 5%? What I always tell my students is you're going to change 5% to a decimal. So 5 divided by 100, and that's going to become 0.05, and then you're going to put a 1 out in front of it. You add 1. So 1 plus 0.05 is 1.05. If you multiply by 1.05, you will increase by 5%. So what I want to do here is I want to take 2,000 and I want to multiply times 1.05 every year, once a year annually for 7 years. So that means I'm going to do this 7 times. So I'm just going to type into my calculator here. I'll let you do that. I'll do it here on my own. So let's see. When we type in 2,000 times 1.05 to the power of 7, I come up with $2,814.20. Just key it in the way that it looks. That is compound interest. Now, usually, we're not going to be compounding annually. In the second example here, I want to do one where we compound quarterly, which means 4 times a year we're going to give you interest. Well, if we give you, in this problem, 4,000 is invested at an annual interest rate of 8%. That's how much we get for the whole year. But we're going to give you interest 4 times a year. Well, that does not mean we're going to give you 8% 4 times a year, because then you'd be getting 32%. So instead what we have to do is we have to take this interest rate, which is the annual rate, and I have to divide by 4. Because each of those 4 times, I'm going to get 1/4 of this interest rate. So that's 2%. So we're going to multiply here by 1.02, not 1.08. I'm starting with $4,000. I'm going to multiply that times 1.02 until I cover a span of 5 years. Well, if I'm doing this quarterly, which is 4 times a year, for 5 years, ask yourself, what power do I need to do this? How many times do I have to multiply by this number? Well, 5 years, 4 times a year, equates to 20. So when I type in 4,000 times 1.02 to the power of 20, this becomes $5,943.79. So here's one for you to try. I encourage you to pause the video and try to calculate this, and then resume. So what this one works out to be is, since it's 6% annual interest but compounded monthly, that's 12 times a year. So I have to take the 6% and I have to divide it by 12. When you take 6 divided by 12, you get 0.5%. 0.5%, when we change that to a decimal, is 0.005. So my multiplier is going to be 1.005. And we're starting with $5,500. We're going to do this for a total of 3 years. But remember, you're doing this monthly. So what exponent do we need? If you're doing it monthly for 3 years, that will happen 36 times. 3 times 12. 12 times a year, 3 years. So I type this in, 5,500 times 1.005 to the power of 36. And this works out to be $6,581.74. That's compound interest. Here's the end of video 2.